In this video, we are going to extend our conversation that we've already been having about points and slopes, and now move into equations of lines. And so the first thing I'm going to ask you to do is consider this question: similarities and differences between these two equations. So I'm just going to give you two equations, and your job is to examine them and identify any similarities and differences they may have. The first one is x plus 2 is equal to 5. The second one is y equals 2x plus 1. So take a moment, examine those, and identify anything that those two equations either have in common or differences that they have. So when I do this exercise in a face-to-face class, a lot of times my students will shout out, well, they both have equal signs. They both have plus signs. They both have an X, if we're just looking at similarities. They're both equations. Okay. If they talk about differences, one of the things that they always point out is that the one on the left has just one variable, just an X. And the one on the right has two variables. It has an X and it has a Y. That right there is the primary difference between these two equations that actually matters. So the first equation we could solve. And so go ahead and solve that. If you think about what we talked about earlier in section 9.1, solving an equation, do you remember what it means? Do you remember the definition for solving an equation? It means find the value of the variable that makes that equation true. And so if we subtracted 2 from both sides, we would get x is equal to 3. And so if we take 3 and plug it back in there, we get a statement that says 3 plus 2 is equal to 5, which is a true statement. And then I always ask, are there any other numbers that you could plug in for x that make it a true statement? After some consideration, everybody says, no, it's just 3. 3 is the only solution. So this equation has one solution. And remember, a solution is the value of the variable that makes this original equation true. Okay, that's an incredibly important concept to where we're going in this video. There's one solution. Now we come over to this equation. And my question to you is, let's talk about solutions. So what's the solution to this equation? Consider that. Consider what it means to be a solution. A solution is something that makes it true. Well, this might require us to think about this a little differently. We have two different variables in this equation. In order to determine whether or not it's true, we need to not have any variables. We need to just have a statement involving numbers like this one, 3 plus 2 equals 5. We have to get something over here that looks like that. So can you play with your X's and Y's? Can you find a value of X and Y that you could put in here and here so you end up with a true statement? See if you can come up with some numbers that you could plug in there that give you just numbers then in a true statement. Maybe you came up with this. This is one possible example. Maybe you came up with this. Take a look at those numbers, 5 and 2. So if we put the rest of the problem back together and just look at the 5 and the 2, does that give us a true statement? 5 is equal to 2 times 2 plus 1. Well, yeah, 2 times 2 is 4, and 4 plus 1 is 5. So this is a true statement. So if I use the number 5 as my y value and the number 2 as my x value, then what I get is a true statement. So now my next question is, can you come up with other combinations of x's and y's that could possibly make it true? Maybe you came up with this. Maybe you came up with 3 for y and 1 for x. 2 times 1 is 2, plus 1 is 3. Maybe you came up with this. 7 is equal to 2 times 3 plus 1. Again, if the x is 3, then 2 times 3 is 6, plus 1 is 7. So what I hope you're starting to notice is that in each of these equations, you needed to have a combination, a pair of x's and y's. So this first one, we had to have x equal to 2 and y is equal to 5. Two different numbers, one for x and one for y. And the same thing for this next one. For this next one, we had to have x equal to 1 and y equal to 3. Again, it's a pair of numbers that go together. And then for this last one, x was equal to 3 and y was equal to 7. Where have we seen pairs of numbers before in our current conversation? Ordered pairs. Remember our conversations about ordered pairs? Remember when we were plotting points on a graph and we had to say they were an ordered pair, an x and then a y value paired together? That's what we're doing here. We're pairing x and y values together that would make this equation a true statement. And when we write them as an ordered pair, they then become something we can put on a graph. So now what I want you to do is get out a graph paper, and we're going to take these 3 points and we're going to put them on a graph. So here you will see those 3 points plotted on a coordinate plane, 1, 3, 2, 5, and 3, 7. And we start to observe things. One thing you might notice is that they all fall in line with each other. And if we connect them all with a straight line, it looks like that. So I'm going to bring that image over to our normal whiteboard. We're going to come back and talk about that in a moment and what that means to us. But I have to kind of wrap up this conversation going back to our original equations here. In this first one, I just want to remind you that we solved x plus 2 equals 5, and we got a single number as the solution. There was only one solution. With this one that we're working on now, y equals 2x plus 1, it had 2 different variables. And what we discovered is that we found 1, 2, 3 solutions that came in pairs, but we could continue that list really forever. As long as you give me a number to insert in there for x, I can multiply it by 2 and I can add 1 and get a new number for y. That would become then a pair that represents a solution. So this equation had one solution. This equation actually has infinite number of solutions. You can extend the list of solutions forever. So that presents a little bit of a problem. What if you want to know all the solutions? Again, this one is easy. It's just 3. But this one, I could go on forever. That's where the graph comes into play. That's where that line that we drew here comes into play. Now, we found 3 solutions. This point, and this point, right? Remember those 3 pairs of numbers, 1, 3, 1 for the x, 3 for the y, 2 for the x, and 5 for the y, and then 3 for the x and 7 for the y. Those pairs were all solutions. Remember this? They all were solutions to this equation because they made it true. Well, guess what? There are more solutions on this line. This point right here, for example, x is 4, y is 9. Here's that equation again. If I plug 4 in for x and 9 in for y, guess what? It gives me another true statement. Here's another solution. 5 and 11. Here's another one. 0 and 1. And guess what? Every other point between them also makes a solution. I could go to a really obscure point right here that came up to a decimal or a fraction. And that combination, right, whatever this y value is and this x value is, a little more than 4 on the x and around 9.5 for the y, whatever that is, those pair of numbers would also make this true. So it turns out that really every single point on this line, which has an x value and a y value that are paired together, every single one of those points represents a solution. So the line is really an infinite number of points. They're all packed so closely together on that line that there's not even any space between them. And every single one of those points is a solution to this equation. That's what a line is. And it's maybe one of the most important things for you to understand about graphs, right? It's not just that there is we graph a line this way, an equation that way, and make this line. It's that the line means something, and it means solutions, combinations of x's and y's that pair together make that equation true. Okay, so that was a long, I guess, prelude to this section, but it's so important to understanding graphing equations of lines. So now what we're going to do is we're going to transition into how do we actually go about doing the graphs when you don't have all this same information. So we're going to start with an examination of several different lines that are already graphed for you. And you can see them right here. And we're going to observe a couple different things. The first thing we're going to observe is the slope of each line. And if we examine this small little triangle here on this very first line, you'll see that it goes +1 in the right direction and +2 in the up direction. So that means that the slope is 2 over 1. Remember, rise over run, change in y over change in x. So that's a slope of 2. You'll notice that this equation, or this line, has the exact same relationship. It is also going to be a slope of 2. And this line has the exact same slope as well. So it's also going to have a slope of 2. All three of those lines have the exact same slope. And notice how they're all angled in the exact same way. The other thing we need to identify on each of these lines is what we call the y-intercept. So the y-intercept is a very specific point, and it's the point at which your line crosses the y-axis. So it's the point where the line crosses the y-axis. And so those points have already been identified for you on these three lines. Here's the first one. Remember, the y-axis is our vertical axis. So for this one, it's the point 0, 0. For this one, it's this point right here. It's 0, 1. And for this line, it's way up here. It's the point 0, 5. Now, every y-intercept, notice that they all start with the 0. They all have a 0 in that x position. And so every y-intercept has the form 0, comma, and then some other number, the number where it actually hits the y-axis. And we tend to call that number b. So the y-intercept will always be 0, b. So we're going to go through and identify for each of these lines the b part of that y-intercept. For this first equation, it's 0. For the second equation, it's 1. And for the third equation, for the third line, it is 5. So we've gone through, and in all three of these equations, we've identified the slope and the b portion of the y-intercept. Now, how do these two pieces of information help us? Well, pretty much every line except for horizontal lines, or well, really vertical lines. Vertical lines are all going to have the same form. And maybe you recognize this. it is called y equals mx plus b, and it's actually called slope-intercept form for linear equations. And what you might notice already is you should recognize the m and the b. The m and the b should look familiar to you because we've already talked about them. M represents the slope of the line, and b is that y-intercept. So if you know an equation or a line slope and its y-intercept, you can then write its equation. And remember where we started this. We started this with this example, y equals 2x plus 1. Notice how it had a y and it had an x. It had a number in front of that x, and then it had another number added to it. But the y and the x will be part of the equation. So if we go through each of these three lines that we just saw, let me see if I can find a good spot to do it. I'll do it right above them. We're going to use y equals mx plus b. And in place of the m, we put the slope. So it's going to be y equals 2x. And then plus the y-intercept number. Because it's 0, we tend to then just drop that part of the equation off, and we write it as y equals 2x. If it crosses the y-axis at 0, we don't need to write plus 0. For this middle equation, it's y is equal to 2 for the slope times x. But now we have a y-intercept of 1. So it's going to be y equals 2x plus 1. The third equation is y is equal to, this time it's 2x again, but it's plus a y-intercept of 5. And again, every point along this line would then be a solution to this equation. So this is how we can take a line, identify its slope, identify its y-intercept, and use those two pieces of information to go back to what the equation is for our line. The one exception to this is would be a horizontal line. So let's just pretend that we have a line that looks like this. And it's going to 1, 2, 3. So it's going to cross the y-axis at 3. So do you remember, we talked about this before, what the slope of a horizontal line is? The slope for a horizontal line is 0. M is equal to 0. So if you try to use slope-intercept form, y equals mx plus b, what you would have is y is equal to 0x plus, and in this case, our y-intercept is the point 0, 3. So 0x plus 3, this really just then turns into the number 0, because 0 times anything is 0. And all we're left with is y is equal to 3. The x term goes away, right? The x term goes away. The other situation that is unique is, as I noted before, a vertical line. So let's say we have a line that looks like this. It's a wobbly line, but that's all right. 1, 2, 3, and 4. So -1, -2, -3, -4. Now, you may also recall that the slope of a vertical straight up and down line, remember how it was undefined? And so there actually is no slope. So this is the one case where we can't use slope-intercept form for a vertical line, but I'll bet you can take a good guess. Look at the problem we just did. The horizontal line was just y equals 3. And that's because every point on this line has a y value of 3. For instance, this point over here might be 5, 3. We already identified this point as 0, 3. And maybe this point right here is -2, 3. Every point has a y value of 3. And so the only rule for the equation is that y is equal to 3. So what do you think this equation might look like? Notice how it crosses the x-axis at 4, 0. If you put a couple other random points on this line, this one might be, I'm sorry, it's not 4, it's -4. This point might be -4, 5. And a point down here might be -4, -3. Notice how in each case that x value is -4. So your rule for this vertical line is that x must equal -4. And so that is the equation of that line. There actually is no y in the equation. And so horizontal and vertical lines have to be treated just slightly differently. Again, a horizontal line will always be y equals wherever it crosses the y-axis, and a vertical line will always be x equals wherever it crosses the x-axis. And so just to kind of wrap up this part of the conversation, slope-intercept form of the line, in general, is y equals mx plus b. M and b are constants. A constant is the opposite of a variable. Variables change, constants are just numbers. They don't change. M is the slope and b is that y-intercept. So let's go ahead and try to do a couple more of these, except what we're going to do is turn it around the other way. So if I give you an equation, can you graph it? So go ahead and find some graph paper and or just sketch something. And I'm going to say y is equal to -3x plus 4 is one equation, and y is equal to 2/3 x minus 1. So see if you can use what we've already learned and see if you can figure out what the graph of those lines might look like. Take a few moments to try that. So maybe you struggled with this. Maybe you figured it out. That's fine. Either way, I just wanted you to play around with this. So when you are given an equation that's in slope-intercept form, first make sure that it is. Does it fit the form y equals mx plus b? It does in both cases. Note that -1 is the same thing as plus -1, and so it's still in that same form. So how do we do this then? I'm just going to write our y is equal to mx plus b right there. So what do we know based on the form? We know that the slope m is equal to -3. That's this one. And b is equal to 4. So one thing that tells us b is 4, that means the point 0, 4 is a solution on the graph. That's that y-intercept. The other thing we know is that if a slope is -3, that means that the rise over run is equal to -3 over 1. Remember, a slope of -3 can be stated as -3 over 1 when we put it as a fraction. So these are the two really important pieces of information: the y-intercept and what our slope looks like as a fraction. When we're trying to graph a line using this form, we always start with the point that we know. 0, 4 is a point on the line, so we're going to start right there. I'm going to put that point on our graph, the point 0, 4. Then we have to apply this slope, -3 over 1. So what that means is for every one place we go to the right, this is a positive direction. For every one place we go to the right, we're going to go 3 spots down. So as I go 1 spot to the right, I'm going to go 3 spots down, and that's going to be where I make my next point. Let me delete my arrow, and this is going to be my next point. Now, I always recommend making multiple points, at least more than 2. I'm going to repeat the process. I go 1 to the right, and I count 1, 2, 3 down. I count 1 to the right, and 1, 2, 3 down. The more points you have, the more accurate your graph will look. I also like to go back in the other direction because the fraction -3/1 can also be written as 3/-1. Remember, in a fraction where the negative goes doesn't necessarily matter. If you view it like that, it's working your line back this way, oops, where if you go one spot back to the left, you have to go back three spots up. Again, they help extend your line to the left. I think that's enough points. Now, again, I'm really bad at drawing a nice straight line, but I'll do my best. So we draw something that looks like this. It should be perfectly straight, and that's not too bad. Okay, so that's what our line looks like. Arrows indicate that it extends both directions infinitely. Notice that when your slope is negative, remember how we talked, it goes down. As you read your graph from left to right, this is going down. So we just graphed the line. So now if you got stuck on this one, see if you can do this next one. Maybe pause the video if you didn't quite get that one and try this one instead. Think about where we start and what we have to do. What information do we have? We know our slope is 2/3, which means our rise is 2 and our run is 3. We also know that b is -1. This is the b, which means our y-intercept is 0, -1. So let's start with that point. Always start with the point that you know is on the line. That's going to be that y-intercept. So we're starting at 0, -1. With the slope of 2/3, our rise is 2 and our run is 3. So for every 3 spots we go to the right, we have to go 2 spots up. And that's going to be our next point. Let's do it again. 3 spots to the right, 2 spots up, make a point. 3 spots to the right, 2 spots up. They should be all falling in a nice straight line. Let's go back to the beginning and go in the opposite direction. So if I go 3 spots to the left, I would go 2 spots down. And that helps me make just a longer line going across that y-axis. Let's connect these as best we can. Not too bad. There we go. So that's what our line looks like. We double check. Did we get the y-axis or y-intercept correct? We did, 0, -1. Remember, that's where it crosses that y-axis. Our slope is positive. It's going up from left to right, but this time it's a fraction 2/3. So again, it's 3 across here and 2 up that way. So that's how we're able to graph a line. That's how we're able to graph a line when you've been given that equation. Now, sometimes we run into a problem where we are not given all of the information that we need. And so we have to use some algebraic tools and algebraic tricks to find them. So if you take a look at these two graphs, we're going to start with the first one, and we are going to determine what the equation of each line is. So what is the equation? And so what I would suggest you do is maybe pause and just stare at this and see if you run into trouble anywhere and where it might be. Remember, we're going to put these in the form y equals mx plus b, where m is the slope and b is the y-intercept. So if you look at this first graph here, what were we given? We were given a point here and a point here. And remember, we don't even need to see the graph to figure out what the slope is. We can use the slope formula if we want to, but we did have a graph, so that's nice. So we can see from this graph that the rise is 8 when the run is 4. So our slope is 8/4, and that does reduce to 2. That tells us our slope is equal to 2. So that's great. But what are we missing? We can't see where our y-intercept is. The y-intercept, I kind of wrote my work here in the way. If we extended this, it's going to go all the way down here somewhere, right? This y-intercept would be way down here, but we don't have enough of the graph to see. So what do we do? Well, here's what we do. Here's a little trick. So if we go to our equation that we know our line has to be in, y is equal to mx plus b. We've already identified m. M is 2. So we can start by substituting in that 2. Y equals 2x plus b. Well, remember going way back. If we go way back to the beginning of this conversation, remember this process where I gave you this equation y equals 2x plus 1, and we came up with solutions to that equation, and each one of those solutions had an x and a y value. That means we can substitute any solution into our equation for x and y, and it's going to give us a true statement. So even though our equation has x and y in it, the x and y can be any point that's on the line. So if I go way back down here to this problem we're working on, we were actually given 2 different points that are on the line, which means we know 2 of the possible solutions. Pick one of them. I always recommend picking the one with easier numbers to work with. So I'm going to pick this one, 5, 3. I'm going to let 5 be my x and 3 be my y. And I'm going to substitute those 2 numbers in here and here. Y is 3 and x is 5, just like we did earlier in this video. Then I'm going to fill in the rest of the equation. But note, I don't actually have a value for b. But here's where algebra comes in handy. We now have enough information to actually solve the equation for b by simplifying 2 times 5 and then using the subtraction property of equality, we find out that -7 is equal to b, which means, remember how I drew this little red dotted line down here? And we saw, yeah, that line's going to intersect way down here in the negative land. Yeah, it's going to intersect at -7. And so now we know the y-intercept and we know the slope. So we can go back to our generic y equals mx plus b equation and write it as y equals 2x minus 7. We just used a little help right in here with that one single point that we knew that was on the line, with this one right there. We also could have used this one and it would have worked the same way. Any point on the line will work. So why don't you go ahead and try that? Here's another equation or another line where you can find the slope from this information, but you can't see where it crosses the y-axis. So see if you can find that y-intercept the same way we just did the last one. We'll start with the slope. So I look at these 2 points here, and we see that m is equal to rise of -6 and a run of 3. -6 over 3 is equal to -2. It's a nice integer. But we don't know where it crosses the y-axis. So we use our generic y equals mx plus b formula. I'll write the whole thing down. We know that m is -2. Let's make my negative a little bigger. But we need to find b. The way we do it is we use one of these 2 points. I'll use 5 and 3 again. X is 5, y is 3. 3 equals -2 times 5 plus b. Again, we will simplify the multiplication to be -10. We still have plus b. Then we use the addition property of equality to find that 13 is equal to B, which means our y-intercept is 13. We can now take that information and write y is equal to -2 x plus 13. This would cross that y-axis up here at 13. And there we were able to build our equation. So sometimes you can use missing pieces. You can use information you have to find the missing piece. This is just your tool to do it. So before we wrap this video up, we just need to talk about a couple other little situations that occur with our lines. So we need to talk about parallel and perpendicular lines. So I'm going to just paste a series of lines in front of you. And just take a moment to observe things. Note what you notice, what things have in common, and what they don't. So take a moment to examine this. So when we talk about parallel and perpendicular, we have to know what those things mean. Parallel lines, they never cross. Never cross. They look like this. They look like train tracks. Well, perpendicular lines, they do cross, but they not only cross each other, they cross each other at a 90-degree angle. So they cross at a 90-degree angle, which means they look like a T, right? They don't look like an X, they look like a T. This has to make a perfect right angle. They look, again, like a T. So what we'll do now is examine what happens on a graph with parallel lines and perpendicular lines. I actually noted this earlier in the video, way back at the beginning. I'll scroll back up when we were looking at these three lines right here. I mentioned at the time that all three of those lines were going at the same angle, and they also all had the same what? They all have the same slope. The slope tells you the steepness of the line. And so if lines have the same steepness or slope, then they're going to be parallel. Let me scroll back down. These four lines right here are all parallel. And note their slopes. 2, 2, 2. Actually, it's 5 lines. 2 and 2. All 5 of those lines have the same slope. Also notice these 5 lines. These also have the same slope. So these are also parallel. -1/2. -1/2. -1/2, -1/2, -1/2. But they do have different y-intercepts. That's why we can see them. And so we have 2 sets of parallel lines. But what we also have are 2 sets of perpendicular lines. Because if you look at how these lines are crossing each other, they all do cross at a perfect right angle, a perfect 90-degree angle. These are all right angles. And so if we know that parallel lines have the same slopes, again, 2, 2, 2, 2, and 2, what do you notice about the slopes of the perpendicular lines? 2 and -1/2. They have opposite signs, meaning one's positive and one's negative, and they're also inverses of each other or reciprocals of each other. And so perpendicular lines have opposite and reciprocal slopes. Both of those things have to be true when lines are perpendicular. Their slopes are both the opposite sign. Again, one's going up and one's going down, but then they're also flipped over. They're also reciprocals of each other. And so just to put this in a nice, neat format for you, two lines are parallel if they have the same slope. Again, y equals mx plus b and y equals nx plus c are parallel if m is equal to n. All that has to be equal are those slopes. Two lines are perpendicular if they are horizontal and vertical. I didn't mention that. But if they are horizontal and vertical lines, or if their slopes are negative reciprocals of each other, y equals mx plus b, y equals nx plus c, and if m times n is equal to -1. When things are opposite reciprocals of each other and you multiply them together, they're going to be equal to -1. Just to prove that to you, if I take the fraction 2/3 and multiply it by its opposite reciprocal, -3/2, right? Change the sign and flip it over. We would have -6 on top, +6 on the bottom, and that is equal to -1. And so that is how we can examine the slopes of parallel and perpendicular lines.